All right, so today is kind of the most important lecture you'll probably ever hear in your physics career. Uh, it's sort of this big idea of modern physics and especially modern theoretical physics, where this one principle comes to define really the essence of physics, believe it or not. And it's this idea of the principle of least action. Now, this idea, I'll say it again because it's so important. The principle of least action is probably, in my opinion at least, it's at the heart of modern physics. It's at the heart of physics in general. And it's really, really an important idea. Uh, there are a variety of sources one can look at to learn about this, and I recommend a few. The first one I would recommend to look at, which is a very good and beautiful version, is in this book called The Feynman Lectures of Physics. And the Caltech, it was a 3-volume set when Richard Feynman, the great physicist, taught a class for freshmen at Caltech. So he taught an undergraduate freshman class, a 2-year class, and he covered a lot of topics. And they put all the lectures into a series of books. Now, what's really special about this is that Caltech made these lectures available online for free for the public. So if you type in Richard Feynman lectures, Principle of Least Action, you'll get the piece. And it's really short. He gave a lecture on it. You should read it. And he tells the story about how he was first introduced to this idea in high school. And he also mentions that every time he hears this idea, and every time he looks at it again, he comes up with new things because it's just such a rich idea. It's just such a wonderful and simple and elegant and beautiful and really the essence of physics. So it's a shame that more people aren't here. It almost makes me want to just postpone this thing, but we have to move on because there's so many important questions that one could ask around this principle and this idea. And it's sort of one of those things, it's like a rite of passage. Everyone must know this principle of least action, and everyone must also know this path integral formulation of quantum mechanics, which is where we're going to get to at the end of this lecture. Now, there's another great source on YouTube that I like personally. So Brian Greene, who's a great professor at Columbia and a string theorist, he did a series during quarantine titled Your Equation of the Week, or maybe it was titled Your Daily Equation. And he actually went into stuff really mathematically. Not really, not as much as we're going to. It was a little less mathematical, but if you want the sense of what's going on, you can watch. He did a lecture on the principle of least action. So that goes to show you how important this idea is. Okay, so let's begin. Let's just start from first principles. Let's start from scratch. And if you can, those of you that can turn on your camera, please do, because I don't want to lecture to just black screens for an hour and a half. But okay, so the main question is this. This is really the big question in physics. If I have 2 points in the plane, what is the shortest distance between them, right? This is the big question. Because in physics, all we want, okay, I have 2 points, x1 and x2, they're labeled, and y1 and y2. And the idea is, in physics, our mission is to find out, really, our mission in any physics context, is to find out the dynamics of something, right? It's to find out how an object is going to move from one time to another, how a particle quantum mechanically is going to evolve from one state to another. This is basically the whole point of physics, right? I mean, it doesn't really matter how complicated things get. It doesn't matter how complicated your theory gets. This is what you're trying to do. You're trying to look at some phenomena. You're trying to see how it develops through time. Okay, Now, obviously, the question, the solution would be a straight line. That's what everyone would say. That's the shortest distance between the 2 points, right? Now, this is fine. This is well. But, we have to consider something now. What if it wasn't that simple? What if I had other dynamics here, right? What if I had other dynamics going on in this situation? What would be the best way to sort of, what would be the best way to solve this problem generally, mathematically? Because the shortest distance between 2 points might not always be a straight line. It might be something else, okay? Now, the second point to think about is there might be a variety of paths the particle could take, or this object could take from x1 to x2, right? It's kind of like this. I have many, many different paths I can take to get home. I can take the easiest path from point 1 to point 2. I can sort of go in some random direction, backwards and forwards along my street. I can go this way or that way. I can go in any sort of path, right? So there's a variety of paths I can take. So how can we sum up this problem mathematically such that we get the path of least resistance? Because remember, nature, what we're very fortunate that particles in nature or objects in nature do take the path of least resistance. Okay, they do take the path that is easiest for them to take. So nature will take the straight line, right? But we might not. There might be a variety of things. Okay, so mathematically, what does this problem come down to? I have something called L, okay? I'm going to integrate from x1 to x2, right? And I have this object ds. What is ds? ds is a little slice of this line. ds is a little bit of this line. So it's equal to the square root of dx squared plus dy squared. So it's a little slice of this line. So basically, if I integrate along the bits, right, the little bits of this line, my goal then, mathematically, this statement sums it all up. What I want to do is I want to integrate along each bit of the line, okay? And I want to figure out what value of ds minimizes this integral. In other words, what value of ds will make this integral the smallest value? That will give me the path of least action. That's what we call the path of least action or least resistance, or the most likely path. Does that make sense? So this, I mean, no one can shake their head, so you're going to have to butt in with questions. But this is really the, if you have questions, please ask, because I can't get a sense of what you guys are thinking. This mathematically sums up the whole entire problem. This is it. Okay. Now, I really haven't told you about how we consider all the other paths or anything. I'm just setting up the problem mathematically. Okay, fine. So let's consider the following situation. This is just the most general case. And as you know, I can integrate along each little bit, right? Each little bit I'm going to integrate, and that will give me the path if I integrate along the path. Okay, now let's consider the situation, which is going to be our basic idea. I have a path, x1, x2. Let's say that's the right path. I have y1, y2. Okay, and now I'm going to, well, I want to find the path of least resistance. I have one little bit, ds equals dx squared plus dy squared root, right? And this is a function of y of x, okay? That's very important because this is really telling me the value of my path at each little point. That's a very important distinction to make, that this is a function. Okay, that's all fine and dandy. Now what? Now I'm going to do the following. I am going to say, imagine there is some path that is the wrong path, okay? And we're going to call this the perturbed path, right? So this is some path, y of x, plus an additional kick. We'll call that rho of x. Okay, so now this is the problem. I have some perturbed path. That is the wrong path. The wrong path does not minimize the action. In other words, the wrong path does not pick out the minimum point of the integral. The right path does. Okay, so now I'm going to have this object. I'm going to call it S. Well, before I do that, let's just do the following. So now I have this big capital Y of x is going to equal rho of x plus little y of x. Okay, so this is my perturbed path. Now, we are going to deal with something in this problem called a functional. Okay, what is a functional? I don't know if you guys have been introduced to functionals, or I mean, the idea is simple. We're going to need it here. Actually, this problem now, so now the problem is really straightforward. The problem is, how do we figure out the path of least resistance? Another way to phrase it is, how do we figure out the path that minimizes the action? Okay, I still haven't told you what an action is. I'm going to tell you in a second, believe me. But we want to minimize that integral. We want to find the place where that integral is the least value. That will tell us the path of least action, integrated along the path. Fine. So this is my perturbed function. But now I'm going to deal with something called a functional. Basically, what that means is it's a function with functions inside of it. So there are three things that will characterize my functional. The first thing is this capital Y of x. The second thing is this y prime of x. The first derivatives of the function are also in the functional, which will be rho prime of x plus y prime of x. And the third thing in my functional will be just x, the x values. So these are the three things I need to consider. And if you think about it, that's really those are the only three things I need to think about this problem, okay? So now I'm going to define an object, call it S, right? And S will equal the integral, right? From x1 to x2 of f, okay, of capital Y of x. So this is my functional, y prime of x and x, okay? And remember, this is an integral over x, because all of these things have x dependencies. I'm integrating along the path, and I want to minimize this. What is this? This is my action. So S is called the action. S is defined as the action. And what I want to do is I want to minimize this action. I want to find out where this integral is a minima. In other words, I want to make this another way to phrase. I shouldn't say in other words because it's not intuitive. Another way physicists frame this problem is they want to find the place where the action is stationary. Okay, that's just the terminology. You hear that a lot. So just, we want to make this action stationary. You'll see why that makes more sense as we solve this problem. Okay, fine. These are perturbed paths, by the way. These are variations from the original path, right? So I have my original path, and I have all these random paths plus rho of x, which are variations from the original path. That's why this topic is also called the calculus of variations, or it's called a variational method, because you're taking all of the varied points and solving this problem. Okay, now what I should really do, I should really write this like this. So my original action is y of x, y prime of x, what was the x? Now, what do I actually want to minimize? I want to minimize the varied action, some delta s. Delta s means I'm varying the action. And this thing is going to be a functional of my perturbed paths, or my varied paths, the variations of the original path. Now, what do I want delta s to equal, folks? I want delta s to equal 0. I want my variation to be 0 because I want the original path. Okay, so this is the whole problem we need to solve. It's really a problem of delta s, which are functions of the perturbed, this should be capital Y, perturbed paths, and I want the variation to be 0. Okay, this is really the whole problem. Now I'm going to do one more thing. I'm going to reparameterize these capital Y's. This is just going to make the problem easier. So let's just do one more quick housekeeping. I'm going to make y of x now alpha rho of x plus y of x. You'll see why. This makes the problem easier mathematically. Capital Y of x prime, capital Y prime of x equals alpha rho prime of x. This is just some constant. It's just reparameterizing the path. And x is just x. So this is my reparameterized path. And now my action, s, delta s of alpha now becomes a function of alpha. Because remember, this is talking about the variations. This is really concerned with this. This thing just becomes the same thing. Okay, fine. So this is really the whole problem now. We want to minimize or find out where this variation, delta S, is 0 or stationary. So that's when we say we want to make the action stationary, more technically what we mean is we want to make the variation of the action stationary. Okay, is everything clear up to this point? Because now it's going to go a little rapid fire. This is sort of the conceptual formalism. Now we just have to do some calculating. Anyone have questions at all? Okay. Okay, so let's compute now this thing, the variation. I'll rewrite the action up top. So my full action is a function. It's equal as the integral from x1 to x2 as a functional of y, y prime, and x dx. The variation of the path, which is what I'm actually concerned about, is delta s of alpha. I've reparameterized it. And we have these capital Y's now, which are now have alphas in it, they have x's in it, and all of that sort of thing. This is a problem we solve so many times as physics students that it's just so, you know it cold how to derive this because you do this all the time. Really, you do this all the time. Okay, so now what am I actually implying here? What I'm implying is that this variation is 0. So what actually in calculus, this is a really nice problem because in calculus, basically I want to find a minima here. That's what I'm trying to do. And in calculus, there's a very nice way to find a minima. All you have to do is find out where the derivatives are 0, right? As you guys know from calculus. So basically, one way to solve this problem is let's just make this the derivative of this functional 0 and compute what that would be, and that will make the integral 0 by default, or the variation of the action. So again, this is the action, very important. This is like a generalized action. Okay, so now my claim is if we insist, because in calculus I know that df of my functional d alpha, this should be dy, yeah, dy, because I'm going to different capital Y, but who cares, dy equals 0, right? From calculus, I know this is a minima. My claim is that if I can do this and set this derivative equal to 0, then my action is stationary, so, or minimized, or I found the least action. Okay, that's my claim. And this just makes sense intuitively, mathematically, from a calculus standpoint. It's actually the way you would this is kind of like a minima and maxima problem. It's just a minima and maxima problem on steroids, right? Because now, think about in normal calculus, you're finding the minima and maxima, or like, let's just say I have some function in ordinary calculus. Okay, the thing is going like this, whatever. This is some f of x. you want to find this, so this would be the minima, let's just say, okay? Or the saddle point, right? As you guys have probably heard. This is, I want to know the minima at one point, and that minima will be where df, let's just say dx equals 0. That's where this minima is going to be. However, now I'm dealing with a functional, and I kind of, and what I'm really doing is I'm finding the minima at every little bit of ds along the path. Okay, so it's a much more complicated problem than just, because now I need to find a ton of minima, a ton of local minima. Okay, so now what does my action become? I'm going to get, I'll just keep the delta. So now my action becomes this thing. The variation now becomes a problem of computing this derivative. This should have a prime. Please correct me if you see any mistakes. I really don't have any notes for today's lecture, so if there's problems, just let me know. Dx. Be careful with the y's and x's. They're kind of, it's flexible how I move between them because these are functionals. Okay, now the question is, how do we compute a functional derivative? So I assume most of you have not done something like that. So the rule for computing a functional derivative goes as follows. So df dy is equal to rho df dy plus rho prime df prime, df dy prime. Okay, and for those of you who have never seen a functional derivative and are doubting this rule, take it at face value, look it up. Just look up functional calculus or calculus of variations. You'll see tons of stuff on this. And so what does my action become now? So delta s of alpha equals the integral from x1 to x2 rho df dy plus rho prime df dy prime dx equals 0. Remember that rho is also dependent on x. Rho is the perturbation. Rho is what's making this variation happen, this rho. Okay, I assume everything is fine until now. I'll give people a second to write. That's usually what happens. Okay, now let's do this thing. So let me rewrite the variation up top. Okay, so delta s of alpha is the integral from x1 to x2 of rho df dy plus rho prime df dy prime dx. My variation is 0. Okay. I'm going to focus on this term and I'm going to integrate this. Integral from x1 to x2 of rho prime df dy prime equals what? So I'm going to have to integrate this by parts. Those of you that are in Calculus BC or have taken BC, you learn how to integrate by parts. It's a very simple formula. Here's the formula. If I have the integral of u prime v, that's just equal to u v, evaluated at the boundaries, that's what these brackets mean, minus the integral of u v prime. This is not the standard way people write integration by parts, but it's actually equivalent. We can talk about that tomorrow morning, those of you that want to look into this. Okay, so if I integrate by parts, I get the following thing for this right-hand term. I get rho df dy prime evaluated from x1 to x2 minus the integral from x1 to x2 rho d dx total derivative df dy prime. Okay. Now we have to think about something very important. Let's think about this first term in the integral. Rho df dy prime evaluated from x1 to x2. Now there's a very important thing now. We have to consider, so these are my boundaries, x1 and x2. We have to put a very strict claim, or we have to put a very tight prescription on the boundaries, okay, which is a very important thing to do in physics. So here's x1, here's x2, here are my endpoints of my path, the boundary. And I need to, let's just subscribe our boundary conditions. And there's one thing I need to do, which is super crucial. So I've told you that basically the path can move anywhere. That's the whole idea, right? Rho of x can be anything. Rho of x can move the path here, it can move it here, it can move it in all sorts of crazy ways. But what we need is we need the endpoints to be fixed, right? We can't allow x1 and x2 to move because that is an impossible problem to solve, okay? We need x1 and x2 to be fixed boundaries, or x1 and x2, or the endpoints. And this is really intuitive because endpoints to be fixed. In other words, mathematically, what am I saying? I'm really saying that rho of x1 equals rho of x2 equals 0. I'm saying that rho, the function that moves my path off the wrong thing, is 0 at the endpoints. That is a very crucial thing. This is really my big boundary condition. Because otherwise I can move the endpoints anywhere and I'll have a mess. I mean, it's an impossible problem to solve. These are a special kind of boundary. So when the boundary conditions are fixed, we call them Dirichlet boundary conditions. D-I-R-I, I don't even remember how to spell it. Dirichlet. This is probably wrong. Boundary conditions. This is when your endpoints or your boundaries are fixed. Dirichlet, I'm not pronouncing. There's another kind of boundary condition called Neumann boundary conditions where you can move these things up and down, but we obviously cannot do that here. This is not good in this problem. Actually, in string theory, believe it or not, half the battle is figuring out what boundary conditions. That's kind of like the whole name of the game in string theory. Okay, so this means that this term needs to be 0 because rho at each point is 0. So this thing just drops out of my integral. So this is crucial. So basically, I have just figured out that this thing, integral x1 x2, rho prime df dy prime equals minus the integral from x1 to x2, rho d dx df dy prime, which is often the case. Those of you that integrate by parts, it's very annoying because you always get back another integral. Okay, so now I can sub this back into my variation on the path. Does this make sense, guys? I suppose it does. I'll give you a second to write it down. We're moving at a very fast pace today because I don't, it's kind of, I hope everyone gets this because this is sort of important for everything that we're going to do. Okay, let's move on. I'm just going to erase this now. So now what did I reduce the problem to? Now the problem is really, oh God, what did I have up here? I had the integral from x1 to x2 of rho df dy plus rho prime df dy has really become the integral of x1 to x2 of rho df dy. I don't have to rewrite another integral, it's the same integral, minus rho d dx df dy prime dx. And this is equal to delta S of alpha. So this is really what I've reduced the problem to. I can easily trivially write this in the following way. delta S of alpha equals the integral from x1 to x2. Pull out the rho. Now I'll write the dependence explicitly, and I have df dy minus ddx. Put this in parentheses. df dy prime dx equals 0. And now we're there basically because rho of x can be any wrong path, right? So rho of x can be any wrong path. We're not going to specify it. It can be any perturbation. i.e. wrong path. Therefore, this whole piece needs to be 0. Therefore, df dy minus ddx, df dy prime must be 0, and these are our famous Euler-Lagrange equations. So this is a beautiful, beautiful method from which the physical principles give our Euler-Lagrange equations, which is what we talked about briefly yesterday. Not yesterday, last week. So this is just stunning, and this is kind of intuitive and really elegant because what we're saying is nature will always minimize the action. And that's like a way to say it, right? Nature will always minimize the action. The action tells us the dynamics of the system. The action tells us how the system evolves. And what does the Euler-Lagrange equation tell us? It gives us equations of motion, right? And what do equations of motion tell us? Equations of motion tell us how a system will evolve. So isn't that beautiful? You start off with this physical principle mathematically, or mathematical principle. It's really a mathematical problem. And you have a physical intuition in mind that you want to figure out the dynamics of a system. And it turns out what it tells you, what it spits out is if you solve these things, you'll get the dynamics of the system. And turns out, yes, you do get equations of motion by solving the Euler-Lagrange equations. So pretty stunning. So we've derived them now. A little bit of math, not very complicated. You can probably recreate it now on your own in some way. So this is beautiful, but now let's do some physics. We've kind of just been doing math right now. So now I want to talk about, this is all classical. This is math. Now we're going to do classical Lagrangian mechanics, and that will be a very nice and beautiful entry into the path integral formulation of quantum mechanics. Okay, we did it. So remember from last week, we know what the Lagrangian is in physics. The Lagrangian is equal to the kinetic energy minus the potential. Why is the Lagrangian that? We don't know. I said that last time. It's not like someone sits there and it just works, and this is the construction that we want. And you'll actually see in the path integral how this pops up naturally. Okay, so let's just start off with the most basic example of Lagrangian mechanics, which is the free particle. So classically, the free particle, wow. The Lagrangian is very simple. It's just the kinetic energy is 1/2 mr dot squared. R is a 3-component vector minus u of x, y, and z, whatever the potential is. I can rewrite this Lagrangian in the following way: 1/2 m x dot squared, x dot plus y dot plus z dot whole thing squared. So this thing is really a vector with 3 components, x, y, and z, right? So now I should solve the Euler-Lagrange equations. And what should I get? I should get Newton's second law. I should get F equals mx double dot. Oh, sorry, this should be minus u of x, y, and z. Now, it turns out, we're not going to have time for a break today. But it turns out that we have three Euler-Lagrange equations. We must solve the Euler-Lagrange equations for each degree of freedom. So we have 3 degrees of freedom here, x, y, and z. Degrees of freedom, as I mentioned, are just dimensions. Del L, del x dot. Then I have to solve it for y, right? Del L, del y equals d dy. Del L, del y dot. Del L, del z equals d dz. Del L, del z dot. Okay, so what I'm saying is for each dimension, I have 3 degrees of freedom here, x, y, and z. I must solve the Euler-Lagrange equation separately, and I should get 3 equations of motion, which makes sense. Why? Let's talk about it. If I have the vector f, right? F is a vector, force is a vector with 3 directions, and F equals m r vector double dot. This is really a 3-component equation. There are really 3 equations of motion here. The first one is F sub x equals mx double dot. So the force in the x direction, the x component, Fy equals my double dot, and Fz equals mz double dot. So I really have 3 equations of motion here for this, these are vectors. This is basic physics 1. So now I'm going to generalize this statement. I'm going to write down, so this is really the Euler-Lagrange equation most generally, and say that del L, del Qi, Q sub I equals d dt, del L, del Q sub dot I. That for any general, so Qi and Q sub dot I are what we call generalized coordinates. And this is really important because I can have any coordinate system and my Euler-Lagrange equations work. And I could be anything from 1 to 3 in this situation, right? It could be z, it could be, so Q sub 1 could equal x, Q sub 2 could equal y, Q sub 3 could equal z. Okay, and what I'm saying is for any generalized coordinate system, these will work and give you the right equations of motion. Now I could have r, theta, and phi here. I could have r and phi. I could have some random, I could have spherical. I could have anything here. Okay, so this is the classical picture. So I'm not going to solve all 3 equations of motion. I'm going to solve just the x equation of motion. So let's just do it for x. So x okay, so del L del x is equal to minus du dx. We don't know the potential. Del L del x dot is equal to mx dot. So Euler-Lagrange gives me minus du dx equals d dt. Now these are time derivatives, mx dot. From freshman physics, you should look this up. We know that f sub x equals minus du dx, right? F sub y would equal, I'll just write this here, minus du dy. F sub z equals minus du dz, right? This is just something you should look up, that the force is really equivalent to the derivative of the potential energy in that direction. So this is f sub x. d dt of mx dot is mx double dot. So we get exactly what we expected. Okay. So now we have solved our first problem in Lagrangian mechanics. Well, really our second, because last week we did the harmonic oscillator. But this is like the most simple problem that even high schoolers can, you guys are high schoolers, but you guys are not ordinary high schoolers. So even ordinary high schoolers should be able to appreciate this kind of problem with some basic physics knowledge. Now I want to do one more example, which is a bit more complicated, just to show you how this works. And on the problem set, you have another example called the Atwood machine, which is even more complicated. So you get to work out a really nice problem. So let's do 2D polar coordinates. Let's solve the Euler-Lagrange equations and see what we get. So two-dimensional polar coordinates. In polar coordinates, those of you that don't know, you have a vector r, right? And you have, that's 1 degree of freedom, r, some radius going up. And then you have another degree of freedom, phi, which is this angle you're rotating around. So what could be a good problem for polar coordinates? So imagine I had a rope and I had a rock attached to the rope and I'm swinging my rope. This is a really good problem for 2D polar coordinates. Why? I have my phi, which is the angle going this way, the azimuthal angle, and I have r, I have the radius. So this is 2D polar. If I want to draw a velocity vector in polar coordinates, this would be v equals r dot r hat plus r phi dot phi hat. So we do get an extra factor of r. If you take classical mechanics, you'll derive this. It's very annoying. I'm not doing it. That's the velocity vector. So what is my Lagrangian in 2D polar coordinates? Well, it's 1/2 m r dot squared minus r squared phi dot squared. Okay, that's what my Lagrangian turns out to be. Kinetic, 1/2 mr dot squared. Potential, 1/2 minus, I'll just rewrite this. 1/2 m r dot squared. Kinetic minus 1/2 m r squared phi dot squared. That's my Lagrangian in polar coordinates. You know, if you take classical mechanics, you find out that doing this before, you actually don't learn Lagrangians until usually the middle of the course, and you kind of are pissed because it's so confusing to solve things without a Lagrangian. Because think about it, Lagrangians, we just need energies, and then you turn the crank, right? Before that, this is not as intuitive to figure out something. Okay, so let's do the R. So remember, we have two equations here. We have the R equation and the phi equation. Our generalized coordinates. Remember, we have two dimensions here. Let's do the R equation first. So del R equals what? Del R equals m r phi dot squared. And del R dot equals m r dot. So Euler-Lagrange becomes what? EL becomes m r phi dot squared equals d dt m r dot. So therefore m r phi dot squared equals m r double dot. This is good. Fine. This is F sub r. So this is the force in the radial direction, r. So we get that F sub r equals mr phi dot squared. Okay. Oh God, guys, I'm missing my potential. You should have corrected me. Minus u of r and phi. There's no, sorry, these are both kinetic terms. I forgot. You get an extra kinetic term in polar coordinates from moving this thing around. You get an extra kinetic term. I'm sorry. So let's just redo that, because obviously now the derivatives are going to be a little different. So Euler-Lagrange equations. So del R now with my potential is is minus m r phi dot squared minus du dr. Sorry, brain fart. Del R dot is just mr dot. Okay, so Euler-Lagrange now becomes minus mr phi dot squared minus du dr equals mr dot. D dt mr dot. This thing is mr double dot, and I move this thing over. So minus du dr equals mr double dot plus mr phi dot squared. Just add it over. this is equal to F sub r. So I get that F sub r, the radial component of the force, is equal to mr double dot plus mr phi dot squared. And I get that F sub r equals m r double dot plus r dot phi dot squared. Okay, this is kind of cool. So this is my radial equation of motion in polar coords. What is this telling me? This is really telling me that I have my usual radial acceleration, mr double dot, which is what I expect, but I also get this extra acceleration term, r dot phi, well, should that be, no, there should be an r, no r phi dot squared. So it turns out that mr phi dot squared, you should look up all this stuff online. So then you'll really appreciate how cool this method is. This is called the centripetal acceleration, which actually is very intuitive. You would expect another acceleration term. You would expect another this is centripetal, right? So it's a force that comes from this circular motion, which is what you would expect because you have this phi degree of freedom here. So you would expect another acceleration term, and it turns out it takes this form. Okay, any questions? Okay, so we did the R equation. Now let's do the Phi equation. And we got new physics. We derived new physics from this Euler-Lagrange method. And this is the equation of motion, right? This is really the equation of motion, which is pretty neat. Let's do the Phi equation. Wow, I cannot believe I forgot that potential. Very annoying. Okay, Phi equation. Okay, let's turn the crank. Del L del phi is what? It's just minus du d phi. Okay, del L del phi dot is m r squared phi dot. Okay, so my Euler-Lagrange becomes what? It becomes minus du d phi equals d dt m r squared phi dot. So this one's actually a little more complicated than it seems. So we know that f vector equals minus nabla u. What does this mean? This is basically a condensed version of what I just showed you. In Cartesian, so let's just do this in Cartesian. We know what nabla means, right? It's just the partial derivative in each direction. In Cartesian, as I just showed you, f would equal what? It would equal minus du dx plus du dy plus du dz. Okay, this is nabla. Now in 2D polar, I don't have x, y, and z. I have r and phi. However, because of this nuance in the velocity vector, this is not an exact expression. Now f equals minus du dr, which is fine. We just use that for the r equation of motion, but it's actually equal to plus 1 over r du d phi. So that's f in 2D polar. So I get that 1 over r. So it's a little pesky. So f phi, right, the phi component of the force, the azimuthal component, is really equal to minus 1 over r du d phi, right? So here I only have minus du d phi. Therefore, this object is equal to r times f phi. Okay, so you get the extra factor of r, but actually that's what makes this right. And turns out in classical mechanics, Rf phi is actually equal to this thing called gamma, which you will know from high school physics is called the torque. Now this is intuitively going to make sense because I left this in this form because mr squared phi dot is equal to L in classical mechanics, which is actually the angular momentum. Wow, so this gives me a very intuitive picture. So what do I actually derive as the phi equation of motion? What I actually derive is that the torque is equal to dl dt. This is my Phi equation of motion, which you should know from freshman physics, that the torque is really equal to the rate of change in angular momentum, right? In this angular direction, how I'm turning this thing. So this is beautiful. I mean, that it pops out. Now, obviously, look up that this stuff is true. These are equalities, and see how people get them in freshman physics without Lagrangians, because obviously you don't use Lagrangians in freshman physics. Okay, folks, so these are my two examples, and you're learning Lagrangian mechanics, which is super amazing. And you have an example on your homework. And I'm actually going to send out an email. I actually want everyone to do this homework. I actually am probably going to ask Gabe not to do a problem solving session for it. I might want to treat it like a little quiz, just because it's so, this topic is just too important, especially for those of you that want to do research. Okay, excellent. Let's move on to quantum mechanics. So that was classical mechanics. We used the principle of least action. We derived equations of motion in two situations, free particle and 2D polar chords. We derived the Euler-Lagrange equation, and we're done. That is the classical picture. Does anyone have any questions? Sorry, we don't get a break today. There's just too much material. And then on top of that, Gabe is doing double time today, because not double time literally, but figuratively, because there's two p sets that are due. Okay, let's talk about quantum mechanics. So same idea. Now they're talking about a quantum mechanical particle. Who came up with this idea? Two guys, Dirac and Feynman. Feynman really took it next level, but Dirac kind of had the idea at the beginning. So let's say we have a path. I'll forget the dashes. This is some time-dependent path, okay? Let's say this is the right path. Now the quantum mechanical particle has a variety of paths it can take. Right? However, in quantum mechanics, we have a big issue, because now in classical mechanics, the wrong paths we could sort of toss out. We can't do that in quantum mechanics. Each path will have a probability of happening. Obviously, the crazy paths will have an unlikely probability. The straight line path will have the most probability. And each path will contribute to the probability amplitude. Okay, so now we're working with probability amplitudes, right? It's quantum mechanics. Each path will contribute to that amplitude. It will give some probability. The path that is most likely will contribute the most to the probability amplitude. Oh, good, Bob. You just came into our discussion of quantum mechanics. We did all of classical mechanics now, so you came at the right moment.
All right. Oh, that's right.
Okay, so look, I'll start over for Bob. You have 2 points, and the particle can take a path. Okay, there is one correct path that the particle will take, right? That is the path of least action, as we've just discussed. However, it's not that simple in quantum mechanics, because now we're dealing with probability amplitudes. There's a probability that it will take the right path. That is the most probabilistic path. However, there is a probability that it will take a variety of paths, okay? That it will take a variety of paths. And each path, the wrong path, the right path, will contribute to that probability amplitude. So this is the idea of the path integral now. Okay, the path integral is basically trying to solve the problem of least action for quantum mechanics, and trying to get equations of motion and trying to figure out what we're trying to solve. Trying to figure out how the particle evolves from one state to another, one point in time to another. Again, if I have the right path, the idea is I'm going to integrate over each little bit. each little bit, and we're going to call these little bits delta t, each little bit of time, I'm going to integrate over. That's the whole idea, guys. Very intuitive, very beautiful. Like I keep saying, this is honestly probably the most beautiful idea in all of physics. There's really nothing more beautiful. Okay, but before we solve this problem, I want to show you. So basically, any equation in physics comes from an action, and if you minimize the action, you can get anything in physics. Okay, what we just did. So let's write, what are the actions of the world? Okay, I just want to show you this because we're going to see a lot of these in the future. You can get any equation. So here's the action for electricity and magnetism. Minus a 4, F mu nu. What are these F mu nus? You'll find out. Minus J mu A mu. There. You minimize this action, you're going to get the Maxwell equations. You get electricity and magnetism. Such a beautiful condensed statement. That's why I say you start off with one action, you get everything in physics. Everything, literally. General relativity. S, the square root of d4x minus the square root of this thing g. That's it. That's it. That's all you need. Now, obviously, this is very condensed. I don't want to be so naive. But honestly, this is GR. So this is GR. This is E and M. This will give you the Maxwell equations. Okay, scalar field theory. S equals the integral d4x, 1/2 d mu phi squared minus 1/2 m squared phi squared. This is scalar field theory. This will be what we work with a lot. Okay, we're going to get an equation of motion from this. Really, the equation of motion we'll get is box plus m squared phi. We're going to get something called the Klein-Gordon equation. I'll tell you what box is when we get there. Okay, scalar field theory. Spin zero field theory with no fermions, only bosons. A scalar Q of T. No interactions either. Quantum field theory is bad. Okay, string theory. You know, everyone talks about how complicated string theory is. Here's string theory. Here's the action. D tau, d sigma, square root of minus gamma. That's it. That's string theory. Obviously, this is very innocent. This is such an innocent little thing. It's very annoying to. Here's string theory. There you go, guys. We just saw this is called the Nambu-Goto action. Nambu-Goto action. Written out in full form, the string theory action is still not that complicated. It's like this capital X dot squared, X prime squared minus X dot X prime squared square root. That's the real, that's what this is equal to. And actually, these are even longer things, but that's okay. Here's the string theory action, okay? And now you're going to say, this is intuitive. Here I have d4x, so now somehow I'm working in space and time. So actually, yes, special electricity and magnetism is a relativistic theory. It's consistent with relativity, special relativity. That's why I wrote a d4x. And here I'm working somehow with two parameters, tau and sigma. Okay, so string theory, I'm working with some tau and sigma. Okay, special relativity. We're going to see this action pretty soon. S equals minus mc integral ds. This is special relativity. Obviously, in the relativity class I taught at the library, we didn't see this. It's a little complicated, but really it comes from an action. The gamma comes from an action. The equations of motion comes from an action. So here we go. Oh, and I could even write one down for quantum electrodynamics, quantum chromodynamics, which we will do, Yang-Mills theory, which we will do. So all of non-abelian gauge theory, black holes, wormhole, anything. Every damn thing in physics, every damn thing can come from an action. So in a sense, there's an elegance to theoretical physics. There's an elegance to the idea. And the idea is really, really profound. I mean, really profound. So that's why this class is, as I said at the beginning, is probably the most important physics class you'll ever take. Okay. Everyone says string theory. Oh my God, string theory. Then I write down this action. They go, oh, that's not so bad. Then we start to break it down. Then in 5 minutes, they go, no, stop. So, whatever. You want to know an interesting story before we go to the path integral? Nambu and Goto wrote this, and for 25 years, no one looked at it. And then it was originally written down to solve a totally random problem. And it turned out after 25 years, people started to realize you could get elementary particles from this action, which was incredible. Now, obviously, string theory is not testable, really, but at the time, that was a pretty astonishing thing. Who knows? If we do field theory fast enough, which actually I think we're going to start field theory early before January, just because we have so much time, and we basically. I'll put a disclaimer for the people that will watch this later, because everyone needs to watch this lecture. I'm not going to give another talk on Lagrangian mechanics. That was it, what we just did, because that's what I was going to do anyway. So that's that. And then we have to do a discussion on special relativity, which I think we'll do next week. So I think we're going to do field theory earlier, just because field theory, there's so much stuff that I'd rather spend the extra time on that. And really, to tell you the truth, I kind of want to do a little string theory too, just to show you what it's all about, which I know sounds absolutely crazy. It's not, believe me, it's not. The basics of it aren't bad, but it gets bad pretty quickly. But okay, let's do quantum mechanics. So what is the one way? So I want to find out how this state evolves from some QI to some QF, positions, right? These are positions. How do I do that in quantum mechanics? I compute this. This is in the Heisenberg picture, as you all know. That's why that problem set was so important, because it's basically you can start with this statement and derive the path integral. That's what we're going to do. And it turns out this is what we call the transition amplitude, right? It's the transition amplitude from some initial state QI to some final state QF, right? And what is evolving the state? It's the Heisenberg operator, e to the minus IHT, the unitary time evolution operator, which we have all seen many, many, many times in this class, and we have seen in the homeworks, okay? So we really need to solve this transition amplitude, okay, for the sum of all paths. Because remember, each path is going to contribute something to the final amplitude, each path, but there will be one right path that contributes the most. Okay, first thing I'm going to do is I'm going to break this up into little time chunks of delta t, like I said. So QF, e to the minus IH, delta t, e to the minus IH, delta t, dot, dot, dot. We'll have another e to the minus IH, delta t, QI. Oh, a very beautiful, there's a few great places to learn about the path integral. One, you can learn about it from Feynman himself in his book, in his thesis, actually. If you look up Feynman's thesis was on this. This is what he discovered. But I will say Dirac discovered this like 20 years earlier. Dirac just never published it. Feynman probably kind of knew what Dirac did, just saying. Dirac is, those of you that don't know Dirac, go look him up after Titan, and we'll learn the Dirac equation in QED. Just saying, but really Feynman elevated it, formalized it. So this is really Feynman's thing. So you can look at his thesis, it's free online. You can also look at one of the field theory textbooks. So you can look in any field theory textbook will have the path integral derived in it. And you can also look in oh God, no, don't look in any of that. Look in Townsend. I didn't look at it but I heard he has a very good description of the path integral. Also, this is the last topic we did in my quantum mechanics class, so it's kind of fitting. Okay, so I've broken this up into little time segments, delta t, along the path. Okay, and let's just write down our normalization. Our normalization will be the standard Dirac delta function. Okay, now you're going to see all the things we've learned in quantum mechanics are going to be coming back now in this. Okay, and also I have another normalization, delta of q equals the integral, sorry, my legs, the integral from minus infinity to infinity of dp over 2 pi e to the I pq. This is another normalization. And we also have our standard thing that the integral dq delta of q equals 1. So these are just our standard like integration measures, right? Standard normalization, not so important, trivial. Now, what am I going to do? What can I do here? The first thing I'm going to do is I'm going to insert a complete set of position eigenstates. Insert complete set of q position of q eigenstates, which I can always do, as we know. And what do I get? I'm going to get a multiplicative sum, right? Because now I'm going to get a bunch of q's from j equals 1 to n minus 1 of dqj, this integral, all the intermediary q states. Now remember, the way I set this up is really, it's just my doing. You don't really have to set it up in this way. This is just how I want to. So I have a qf, that's where I'm going to end up. I have an e to the minus ih delta t on some qn minus 2. Then I get a qn minus 2 e to the minus h delta t. Now it's going to go to the next state, qn minus 1. Right? Now these two things have to match, right? That's what it means by putting in a complete set. That's what I mean by that. Again, e to the minus ih delta t, right? And then this is going to be what? This is going to be some, we'll just say q, we'll just end this here actually. We're not even going to bother. Okay, and then we'll go to where I want to go actually. And then we have something q2. Sorry, this should be like this. Something q2, right? E to the minus ih delta t acting on q1. Some q1, the next state. Then I get another q1, e to the minus ih delta t, and I get my initial state. Okay, let's break this down. I really didn't do anything really complicated here. It looks complicated. All I did was insert a complete set of position eigenstates. Those position eigenstates can be any value. They can be an infinite value of things, right? Therefore, I have these multiplicative sums. I have to end at QF. I have to start at QI. That's what the transition amplitude tells me, right? All right, that's what I'm computing, the transition amplitude. I've broken it up into little delta t's, and in between, I've inserted complete sets of states. Okay, that's what I've done. Okay, now this is kind of like the key expression we want to calculate. This is really the key thing we want to calculate now, right? Okay, I'm going to rewrite it up top just because it's pretty important. Please stop me if you have questions. Be happy to answer them. Q1 acting on Qi. This is our beast. Now, what am I going to do? This is a very complicated problem. What I'm going to do is I'm going to focus on one term. I'm going to try and compute that. And then I just have to reiterate it over and over again. Then I can plug it back into this thing. We'll call it star. That's really all I have to do. Then I can just reiterate it over and over again. So let's focus on one term. We'll call it Qj plus 1 e to the minus IH delta t on some Qj on the next state. Okay, let's use the Hamiltonian for the free particle. H hat equals p hat squared over 2m. This is an operator. And let's insert a complete set of momentum eigenstates. So what are my rules? What does that mean? So complete set of momentum eigenstates means that dp over 2 pi, this thing, equals 1. This is a complete set. It really should have a sum over the p states, but whatever. And then the other two things is, remember, we have to remember this identity. Qp equals e to the I pq. This is what we learned from unitary operators. So all of the things that we've learned are coming back now. And then we also need to, I insist that this momentum state we're putting in is really a momentum eigenstate that solves this eigenvalue equation. Okay, beautiful. So this is like our whole quantum mechanics sequence plugged in. Now we insert the complete set here. So after inserting a complete set of momentum eigenstates into this thing, we're going to get the integral, obviously, from dp over 2 pi. And then we're going to get qj plus 1 e to the minus I h delta t. We get that first p state, we get the second p state, and we get qj. Okay? Remember, I'm focusing on one contribution. This is only one individual contribution to the transition amplitude. It's not the whole amplitude. This is not the whole thing. This is one piece. Okay, now I can manipulate this. I can rewrite this as dp over 2 pi. Yeah, I gotta go fast. No, it's okay. I'll go a little over. Gabe will understand. It's dp over 2 pi. Now this unitary, this should really, sorry guys. This should really be I delta t, and then my Hamiltonian, p hat squared over 2m on this. So now this is going to act on this momentum state and give me a momentum eigenvalue. So this p hat becomes a p. So now I've actually been very careful for you guys. Minus I delta t, p squared over 2m. So I've acted it, I pulled it out. Qj plus 1, p, yep, qj. Okay, this is what I'm left with. I'm going to leave this top equation here because this is really the big boy. This is what we have to get to. This is the whole amplitude. This is a piece. And now I can rewrite this thing as integral dp over 2 pi e to the minus I delta t p squared over 2m. And then using this identity, qp equals e to the I qp, I can rewrite this thing as another exponential, e to the I p qj plus 1 minus qj. Okay, and this is my expression. Now, it's really a matter of computing this integral. This is a Gaussian integral, so let's compute it. I'll give you a second to write. So I have a trusty formula that I can use. This is just a Gaussian. So from minus infinity to infinity, if I have a Gaussian of the following form, Let me think. I have to always remind myself. Dx e to the, is it a minus sign or? Yes, 1/2 I ax squared plus I jx. We have this kind of integral. This is just a formula. I get 2 pi I over a to the 1/2. And we're going to be proving a lot of these in field theory. E to the minus I j squared over 2a. So when you use this formula, you can solve this integral. I'm not going to do all the algebra. You figure it out. It's too long. You get the following. You get minus Im over 2 pi delta t to the 1/2 e, right? The Im qj plus 1 minus qj over delta t or 2 delta t? Over, no, I have a 2, sorry, over 2 delta t. My mistake. There is a factor in the formula. So that's my integral. Now I can manipulate this a bit. Let me just look at it for a second, see what I can do. So this factor is going to stay the same, definitely. So what do I want to do with this exponential? That's what I want to think about. Yes. I delta t m over 2 times m over 2 times qj plus 1 minus qj squared. That's what I want to do. Believe me, that works. I'm pretty sure. Oh, shoot. Wait a second. No, it's wrong. Sorry. Sometimes in my head, I go a little fast. I need a over delta t. Yeah, because I have a factor of 2. Okay, and we're done. We computed that integral. We computed that bit, which is super hard, but we did it. And so we found out that 1 bit of the transition amplitude for the free particle, let's not forget, we're working with the free particle, is minus Im over 2 pi delta t to the 1/2 e to the I delta t m over 2 qj plus 1 minus qj over delta t squared. This is 1 bit of the transition amplitude. Now we just have to plug it into star and reiterate it. So now I plug into star, I get the multiplicative sum n minus 1 from k equals 1 to n minus 1. I'm going to make this a k, integral over qk, dqk, sorry. We're going to call these k's because I have too many variables. This factor stays the same, minus Im over 2 pi delta t to the, now n over 2, because it's going to depend how many paths I have, right? Infinite number of paths. Now I'm plugging this thing in. E to the I delta t m over 2, and then a sum over these q's. This has no paths. These have no paths. It's a sum over paths. So now I get this summation sign here. I get j equals 1 to n minus 1. This is all in the exponential. Qj plus 1 minus qj over delta t squared. Okay, this is my expression now that I just derived. I'm going to rewrite it up top because this is really the meat of what we had to do. I have 6 minutes. I think I'll get to the punchline. Let me just rewrite this. So now my expression Remember, this is the transition amplitude for the free particle minus IHT QI equals multiplicative sum n minus 1 k equals 1 integral dqk minus im over 2 pi delta t n over 2 e to the I delta t m over 2 sum n minus 1 j equals 1 qj plus 1 minus qj over delta t squared. Whew. That's the expression. Oh, and remember, h hat equals p hat squared over 2m. Oh my gosh. See why we saved this for last? Now, we're almost there. We've really reduced this problem beautifully. Now I have to give a phone call to Newton and Leibniz, my calculus buddies. Now I have to take this in the continuum limit, as you guys love from calculus, because now I have discrete chunks of delta t. But now I want delta t to go to 0. So now I want to make this continuous, right? That's what calculus does, right? We take those discrete bits of time and make them really, really tiny so we really get a continuous path that we're integrating over. That's the whole name of the game. So now, a la Newton and Leibniz, what do we get? We get that this bit, delta t sum from j equals 1 to n minus 1 becomes now an integral of dt. Right now that sum, that iterative sum over little bits, the bits are so tiny that it's really an integral over a continuous space. Man, I love calculus. It's so intuitive, right? Because you're taking this like really complicated thing and you're saying, let me take it in the continuum limit as delta t goes to 0, right? And it looks like if you take it in the continuum limit, it looks like you have a straight line, a continuous line. There's no bits at all. The bits have disappeared. Now, the second thing we know from Newton and Leibniz is that this term, qj plus 1 minus qj over delta t squared really becomes a time derivative. So this bit becomes q dot squared. Sorry, Gabe, you're going to have to give me 5-10 minutes because we're almost at the punchline.
Oh, no worries, no worries.
I'm going at lightning speed today. Lightning speed. We did all of Lagrangian mechanics in like the first half. Okay, so Newton and Leibniz have come in handy. I've taken delta t in the continuum limit of my transition amplitude. And now my path integral, this is a path integral, really, in some complicated form, really kind of becomes easy. And remember, this is for the free particle Hamiltonian, no potential. So what does my transition amplitude become? It becomes qf e to the minus IHT qi, right? The whole problem we're trying to solve, these things kind of stay there. And then this thing becomes this. It becomes e to the I, okay, integral now from 0 to t, whatever my time is, right, dt, right, of 1/2 m q dot squared.
Kyle,
Yes.
your camera's
camera's off.
on.
Oh, sorry. Thank you. Wow, this is kind of phenomenal. We start off with this free particle Hamiltonian, and we get the kinetic energy. This is really odd. This is the transition amplitude. This is the integral over paths. Now, this thing looks really complicated. This is really like, I like to call it, Gabe, would it be fair to call this crap like normalization fluff?
I think so. I
Yeah,
mean,
this
it is what it is.
Solve into like this thing. It's like a capital D Q of t. Okay. And this is what we call the integral over paths, really. This is the piece that is the int over paths. This is like, it comes up when you're doing computations, but you'll see when you work things out what you're going to do with this. It's not that bad. As me and Gabe have said, this is more like, I don't know, Gabe, how would you describe it?
Sorry, I zoned out. Not gonna lie.
Okay, that's fine. Okay, so we are there, guys. This is it. This is the path integral for the free particle. So the transition amplitude, QF, e to the minus I, ht, qi equals this integral, dq of t, capital D, e to the I from 0 to t, dt, 1/2 m q dot squared. Beautiful. This is it. Now we're going to write this more generally. That's why I need an extra few minutes. More generally, this is not general because we have a Hamiltonian. So let's consider if I have a Hamiltonian, p hat squared over 2m minus some v of q hat. Okay, some potential. This is what you're going to prove in your homework. So I've given you this Hamiltonian. And it turns out when you write the path integral, you find that the transition amplitude for this thing is the integral dq of t, e to the I from 0 to t, dt, 1/2 m q dot squared minus v of q. You find out, and what is this? This is the Lagrangian. Okay? You find out that naturally, when you use this Hamiltonian, which you will do in your homework, you get the Lagrangian, and that's the general form of the path integral. So you get that QF e to the minus I ht qi generally, so this is really what the path integral is solving, dq of t e to the I integral 0 to t Lagrangian q and q dot. I forgot to mention, the Lagrangian is really a functional of positions and velocities. Okay? That's all you have in the Lagrangian. So any Lagrangian can be written as q and q dot of I. Okay? So this is it. This is the path integral. I'm going to show you one more quick thing and give you two more quick notes. So the one quick thing I want to show you is a lot of times in field theory, we do this thing called a Wick rotation. So I'm just going to show you what that is. A Wick rotation, and the reason I show you this is this will become important in context we use it in. We let t go to it. So it's some kind of complex rotation in the complex plane. Don't worry about the specifics, but basically our path integral now becomes this thing called z. I think it's what, z of q or z of t, or I don't know how people write it. I think they just write it as z. Integral dq of t, e to the 0 to t. There's no more I. Taking care of it, should have a minus sign, dt. And then you actually get this thing, 1/2 m q dot squared plus v of x. This is your Euclidean path integral. This is what we'll use in field theory sometimes, not very often. If you have ever heard of lattice field theory, they use this version of the path integral. Okay, a few notes and then we're done. You will do this calculation on your homework to get the Lagrangian, which is kind of amazing. Didn't have to work out like that. First note, the path integral is extremely useful in quantum field theory. It's not only useful in quantum mechanics, it's extremely useful in quantum field theory, as we will see. Second note, there was this guy named Julian Schwinger, who was very, very friendly, not friendly, who won the Nobel Prize with Feynman. They worked on very similar work, who never used a path integral in his life. He hated it. He said it, he used something called the canonical formalism of quantum field theory. So the point I'm getting at is there's two ways to approach field theory: path integrals and canonically, or old-fashioned perturbation theory. We're going to learn both. And the last thing I'll say is what we really did here was perturbation theory. We really did a technical way to say this is that the path integral is a perturbative expansion. It's a perturbative expansion of paths. That's really kind of the way to frame this. Because what we're kind of doing is, like I said, each path contributes to the amplitude. They're all there. We haven't like canceled out a path. Okay. The only paths that have canceled out are like the paths that are totally opposite from one another, right? They just like cancel out the contributions. But really, we have everything right here, up here. This is the free particle again. This is the Hamiltonian, right? So just put an H in there. We'll see in field theory, these become Lagrangian densities. Who cares? Okay, folks, this is it. Gabe, do you have any last notes you'd want to add? I recommended Townsend, which is, I didn't look at it but I've heard it's a really good way to explore this.
Yeah, no, Townsend has a pretty good blurb. It is chapter 8, if anybody's curious.
Yeah.
But yeah, no, it's pretty fascinating how, like, if you think about it, you're just like adding up paths and you get a formalism that is, like, if you apply this to particularly, now we're talking quantum mechanics, you're just adding together paths and you get a formalism that is essentially identical to like the Schrodinger equation, which is pretty fascinating.
Exactly. And actually, Gabe and I, we've taken a hiatus from it, but in the winter, we're going to work on it more, are working on a project that sort of gets to the core of this. Gabe has really found a way to mathematically and explicitly figure out how to add up these paths, right?
Well, yeah, I wouldn't say that I found the way of it. I figured that Feynman did, and I just kind of
went along for the ride.
Hmm?
But one quick thing, Gabe, you know Dirac actually kind of figured this out before, right?
I did not actually.
Look it up. I read this in a textbook that Dirac started actually with this transition amplitude and got to an expression pretty similar, but it wasn't exactly the same.
Yeah, of course Dirac did.
Of course, yeah. This is exactly. See, so guys, Gabe has the same reaction I had. Of course, Dirac did it because Dirac did everything. Okay. Okay, guys, so that's it. You should give yourself a pat on the back because as Gabe knows and as I know, this is the epitome. This is when you know quantum mechanics. This is really a condensation of everything that we've learned. And it's pretty amazing, elegant, simple. The principle of least action is so beautiful and simple and elegant. I mean, I showed you all of physics in a few statements. I showed you string theory. I showed you general relativity. I showed you field theory. I showed you electricity and magnetism by writing out actions. Okay, guys, I'll be here tomorrow morning. I know Gabe has a lot to cover today, right? Two problem sets.
We have some catching up to do.
Yeah, so I wish you luck. And I will send out an email tonight to the class about this next problem set. I want to treat it almost like a little quiz, just to kind of see where everyone is at. And I think that this next problem set is really indicative of the stuff we've been learning, because I know Gabe really goes through the calculations in depth from what I've heard, which is fine, which is good, which I like. But for this next one, I want to see kind of where your thought process is. And just because this topic, the principle of least action, is literally, in my opinion, the most important thing you learn in physics. I can't think of another just concept that is most important. I don't know if Gabe has something that's more important.
No, I think the principle of least action, it's always been, ever since I learned in mechanics, it's always been the most kind of mind-blowing fundamental thing. Because if you think about it, right, like, how do you derive GOD6 in general relativity, least action? How do you...
square root of minus G, right?
Yeah, it's everywhere. And it's super fascinating to think that, like, if you extremize a path, that's essentially fundamental to all of physics, which is really cool.
Exactly. So I'm really not understating it when I say that. One quick note, and I didn't mention this, and then I swear. Another term for that S equals Oh, sorry. I should also write this. This is important. So the action is really equal to the integral of a Lagrangian. Okay, that's super important. I totally forgot to say that. Q and Q dot. So another way to write out the path integral. Oh God, I should have done this. It's okay. Everyone's here except Lizzie. She'll watch. Is QF e to the minus IHT qi equals integral dq, forget the t, integral e to the is. So that's another way to write the path integral more succinctly, because the action is the integral of the Lagrangian, which you're trying to minimize to get equations of motion, or find the extremal path, or make it stationary, or whatever you want to say. Okay, folks, thank you. See, it's good I spent an extra minute. I remembered to show you this. This is kind of important. And those of you watching, that's important. Oh, and another name for this is called Hamilton's principle, which that doesn't really matter. No one uses that name. But when you learn it in classical mechanics, you learn this as Hamilton's principle. All right, Gabe, take it away. I'll make you host. Thanks again, guys.
Alrighty. Okay, so you have a lot of stuff to get through.